The Sun's corona presents a baffling mystery. The photosphere, which is the visible surface of the Sun, has a temperature around 5,500 degrees Celsius. But just above it, rather than cooling off, the temperature shoots up drastically. The solar corona, the outermost layer, reaches millions of degrees Celsius. This strange temperature jump defies conventional understanding of heat transfer and has puzzled scientists for years. The corona's extremely low density prevents heat from being transferred efficiently from the photosphere. Since the corona is made up of plasma and ionized gas, which are highly influenced by magnetic fields, the rules governing energy transfer here are different from those in ordinary gases. This makes scientists look beyond traditional theories to find answers. One of the most studied possibilities involves Alfvén waves, which are waves that carry energy along the Sun's magnetic field lines. These waves travel through structures like spicules, which are jet-like features that rise from the chromosphere and can dissipate energy in the corona through turbulence or other nonlinear effects, turning magnetic energy into heat. Recently, the Parker Solar Probe has gathered data on unusual structures known as switchbacks, which are sudden reversals in the Sun's magnetic field. These structures suggest areas where reconnection and instability could lead to localized bursts of energy, contributing to the heating of the corona. Another promising theory comes from Eugene Parker, who proposed the idea of nanoflares. These are tiny magnetic explosions that happen frequently, and while each one is small, their cumulative effect could explain the Sun's energetic corona. Specialized telescopes, focused on extreme ultraviolet wavelengths, have been looking for signs of these tiny flares for years. The magnetic field lines of the Sun, which are tightly woven and constantly shifting, create a three-dimensional mesh that can store energy. When these lines reconnect, they release heat in specific regions of the corona, contributing to localized and recurring temperature spikes. Space missions like the Parker Solar Probe and the Solar Orbiter are refining our understanding of these phenomena. While the Parker Solar Probe takes measurements directly from the corona, the Solar Orbiter offers detailed observations from afar, allowing scientists to map the magnetic field and dynamics of the solar atmosphere with incredible precision. Despite advancements in research, computer models based on magnetohydrodynamics still don't fully agree on how much each of these mechanisms contributes to coronal heating. The consensus now is that the heating is the result of several combined processes, with their intensity and impact varying depending on the region of the Sun and its current activity. Understanding these processes isn't just a scientific pursuit, it has practical implications. The corona is the source of the solar wind and coronal mass ejections, CMEs, both of which can have direct effects on Earth. These events can disrupt satellite communications, power grids, and even pose a threat to astronauts. Despite the corona being an extremely rarefied region, it emits strongly in extreme ultraviolet and X-ray wavelengths, which give us valuable insights into its temperature, density, and composition. Solar observatories in orbit continuously monitor this radiation. In certain instances, gamma-ray emissions from the Sun might originate from its outer regions, far from the flare's source. This could occur when protons collide with the surrounding matter in the solar atmosphere, resulting in high-energy photons being produced in a more spread-out and delayed manner. Another potential explanation is that once accelerated, these particles could follow complex, winding paths along the magnetic field lines that wrap around the Sun. This would allow protons, initially accelerated in one hemisphere, to travel across to the opposite side of the Sun, where they might produce gamma-ray emissions far removed from the flare's original location. Despite these intriguing possibilities, the exact mechanisms behind how these particles are confined and transported across such vast distances remain poorly understood and are a subject of ongoing research. Solar magnetic fields are far more complicated than earlier models suggested. Observations show that they are highly structured in 3 dimensions, creating magnetic configurations that challenge the simplistic 2-dimensional models traditionally used to describe solar activity. These complex magnetic geometries could play a critical role in allowing particles to stay trapped in certain regions of the Sun's atmosphere for longer periods of time than expected. As these particles interact with the Sun's magnetic field, they might undergo multiple stages of acceleration. This dynamic process raises the possibility of energy being stored and then released in a way that is much more intricate than previously thought. In response to this, space missions like the Solar Dynamics Observatory, SDO, RSS, Reuven-Ramity High-Energy Solar Spectroscopic Imager, and the FIREM experiment have been systematically monitoring solar gamma-ray emissions. Their data has revealed events that break away from the expected patterns of solar flare activity. In many cases, the light curves, graphs showing the brightness of the sun's emissions over time, suggest that there are several distinct phases of particle acceleration. These phases involve different populations of particles at different times, implying that solar flares may be sustained by a process of continuous injection of particles and their subsequent reacceleration, rather than a single explosive event. This idea of ongoing particle injection and reacceleration during solar flare events is still a new concept and presents a major challenge in terms of detection. Gamma-ray emissions are rare and often indistinguishable from cosmic background radiation. Detecting them requires highly sensitive satellite instruments capable of differentiating between the faint gamma-ray signals from the sun and the noise from distant cosmic sources. However, the growing number of documented gamma-ray events is changing our understanding. What once seemed like an anomaly may actually be a common occurrence that was simply overlooked due to the limitations of past detection technologies. These newly identified events suggest that prolonged gamma-ray emissions might occur more frequently than originally thought, but have been hidden in previous records because of instrumental constraints. With the rapid advancement of space-based missions and improvements in magnetohydrodynamic modeling, scientists are now able to create more accurate three-dimensional maps of the sun's environment, including the intricate paths that particles follow. This enhanced ability to visualize the sun's magnetic field and its complex behavior will ultimately allow researchers to better understand how energy is transferred between distant regions of the sun and how this energy reaches Earth in the form of unexpected signals. The persistence of gamma-ray emissions beyond the expected times and locations of flare activity presents a direct challenge to traditional theories about solar flares and particle behavior. This challenge has prompted the scientific community to rethink existing models of particle acceleration, confinement, and propagation, pushing the boundaries of our understanding of the sun's extreme environment. To fully comprehend this phenomenon, scientists must reevaluate and revise their ideas about how high-energy particles are generated and sustained in such a powerful and chaotic system. The mystery of solar gamma rays is not just a theoretical puzzle. It has far-reaching implications for our understanding of the sun, solar activity, and the mechanisms driving high-energy astrophysical phenomena. This unfolding mystery is forcing a redefinition of solar physics, particularly in the area of high-energy particle dynamics. By comparing the totals, physicists were able to confirm that all the expected solar neutrinos were indeed present. The puzzle was not about their absence, but about the fact that these neutrinos were changing identities as they traveled. This phenomenon, known as neutrino oscillation, happens when neutrinos switch between different flavors during their journey. For this oscillation to occur, neutrinos must have mass, albeit extremely small. This discovery directly contradicted the previous assumption in the standard model of particle physics, which held that neutrinos were massless. This breakthrough forced a re-evaluation of particle physics and earned the 2015 Nobel Prize in Physics for Takaaki Kajita and Arthur B. MacDonald, who conducted the key experiments that demonstrated neutrino oscillation. Though the exact mass of neutrinos remains unknown, it is understood to be incredibly small, millions of times lighter than an electron. However, this minuscule mass is enough to allow quantum oscillations between different types of neutrinos. These oscillations are a collective effect involving billions of particles produced in the sun's core, and understanding them has become crucial for validating solar nuclear models. The proton-proton chain reaction, the primary fusion process in the sun, predicts specific neutrino fluxes at various energies. By measuring these fluxes, scientists can verify the nuclear reactions taking place deep within the sun without relying on light. Light, it's important to note, takes tens of thousands of years to escape the sun's interior due to the dense material it must pass through. Neutrinos, on the other hand, escape almost immediately. They are like direct messengers from the sun's core, offering real-time insight into the fusion processes that sustain life on Earth. Today, facilities like Super Kamiokande in Japan and Borexino in Italy are continuing to refine these measurements. The sensitivity of the detectors has advanced so far that they can now distinguish fluxes from different nuclear reactions within the sun. This is a field that demands precision, and it is supported by years of statistical analysis, with trillions of particles detected to refine our understanding. As solar astrophysics and particle physics converge, they highlight the sun's role as both a natural fusion laboratory and a constant source of neutrinos for experiments probing the fundamental properties of matter and the laws of quantum physics. Moreover, studies of solar neutrinos are helping to calibrate detectors used in other areas of physics, such as the search for neutrinos from supernovae, the cosmic neutrino background, and even exotic processes like dark matter annihilation. In this context, the sun serves as a reliable and constant source for neutrino experiments. The confirmation of neutrino oscillations reinforce the validity of standard solar models, showing that energy production through fusion is aligned with predictions. The observed discrepancies in earlier neutrino measurements were due to instrumental limitations and conceptual misunderstandings, rather than any flaw in our understanding of solar physics. This was one of the greatest triumphs of observational science. Solar neutrinos are among the only direct methods available to study the sun's core. Neither seismic waves nor magnetic fields can penetrate that deeply. Neutrinos, however, carry an unaltered and unfiltered signature of the processes happening in the sun's heart, traveling from the core without interference or delay. Trillions of these particles pass through every square centimeter of the human body every second, leaving no trace behind. These nearly massless and chargeless particles are created during the fusion of hydrogen into helium in the sun's core, the fundamental process that powers the star. Because of their elusive nature, neutrinos are the only messengers that give us a direct window into the sun's deepest processes. Most forms of energy generated in the sun's core, such as light, take an incredibly long time to reach the surface. A photon produced at the sun's center can take up to 100,000 years to escape, as it constantly collides with particles in the dense solar interior. In contrast, neutrinos escape almost instantly, traveling in a straight line from the core to Earth. This makes neutrinos a kind of live signal of solar nuclear activity, allowing us to observe the heart of the sun directly, something even the most powerful telescopes cannot achieve. These particles pass through layers of plasma, magnetic fields, and internal structures, carrying information that no other form of radiation can provide. Underground detectors around the world continuously record these neutrino fluxes, their depth essential to shield the signals from cosmic rays and background radiation. These detectors are housed in giant tanks filled with pure water, heavy water, or other sensitive materials that capture rare interaction events, producing tiny flashes of light when neutrinos interact with atoms. The rate of these detections confirms that the proton-proton chain reaction, the sun's primary fusion pathway, is functioning as expected. There are also secondary neutrino flows, such as those from the carbon-nitrogen-oxygen CNO cycle, which contribute to a lesser extent. By detecting these various sources, scientists can refine internal models of the sun with remarkable precision. Since neutrinos are produced in specific nuclear reactions, they carry an energy signature that reflects those reactions. This allows researchers to not only confirm that fusion is occurring, but also determine the exact proportions and conditions under which it happens. It's akin to analyzing the exhaust of the sun's engine in real time, with atomic-level precision. The data gathered from neutrino observations also shows that the neutrino flux from the sun is extremely stable over time. This suggests that the sun's interior is far more constant than its surface, where fluctuations in the magnetic field and the appearance of sunspots occur regularly. Neutrinos, in contrast, are unaffected by these surface variations or even by the Earth's changing distance from the sun. They travel at nearly the speed of light, and their interaction with matter is so rare that even an entire planet is not enough to stop them. This makes them ideal for serving as reliable indicators of stellar energy production. In addition to providing insights into solar physics, neutrinos also play a crucial role in exploring the fundamental principles of physics beyond the standard model. The confirmation of neutrino oscillations is just one example of how these particles bridge the gap between astrophysics and particle physics. Future experiments, such as Hyperkamiokande in Japan and JUNE in the United States, are designed to push the boundaries of sensitivity and improve the precision with which we can measure neutrino flux and its temporal and spectral variations. This could open the door to a new type of stellar weather forecasting, where scientists can track subtle shifts in neutrino flux to predict solar cycles or identify unusual fusion events. Neutrinos have also been key in studying supernovae. In 1987, neutrinos from the explosion of a distant star in the Large Magellanic Cloud reached Earth hours before the visible light from the event arrived. This confirmed that neutrinos are the fastest messengers of high-energy events, even on galactic scales. In distant planetary systems, directly observing neutrinos is not yet feasible. However, with the Sun serving as a natural neutrino source just 150 million kilometers away, it provides an unparalleled opportunity to test theories and calibrate instruments, making the Sun both a laboratory and a primary source for neutrino research. Unlike larger solar flares, nanoflares occur on much smaller magnetic loops, often beneath the resolution of current imaging technology. Simulations based on magnetohydrodynamics support the idea that such events are not only plausible but likely. These models suggest that coronal loops are constantly filled with magnetic activity at incredibly tiny scales, with frequent small-scale reconnections that generate localized bursts of energy. The cumulative heating from these events could elevate the temperature of the plasma without needing large-scale explosions. However, the challenge lies in translating this theoretical model into observable phenomena. Detecting the signature of these nanoflares remains a key goal in solar research. One approach to confirm nanoflares involves searching for high-energy particles or spectral line broadening, which would indicate sudden heating in the corona. Some studies have already reported signs of plasma temperatures exceeding 10 million degrees in areas of the Sun's atmosphere that do not show visible flares. This suggests that smaller, invisible events are continuously energizing the corona. Another promising direction involves spectroscopic analysis of emission lines sensitive to both temperature and density changes. Instruments like the Solar Dynamics Observatory SDO and IRIS Interface Region Imaging Spectrograph provide detailed spectral data that can hint at heating patterns consistent with the nanoflare theory. The key challenge is to match these spectral observations with precise temporal and spatial data, which would allow scientists to confirm the existence of nanoflares. The concept that the corona isn't steadily heated but rather crackles with intermittent energy aligns well with the nanoflare model. Each nanoflare may be imperceptible on its own, but collectively they form an invisible furnace, continually energizing the Sun's outer layers. This idea forces us to reconsider the nature of stellar atmospheres, no longer viewing them as passive, static layers, but as active, dynamic, and turbulent systems constantly in motion. In addition to their role in heating the corona, nanoflares may also play a crucial role in accelerating the solar wind. The energy released in these tiny magnetic explosions could disturb the surrounding plasma and help propel particles outward, contributing to the large-scale outflow of material into space. This potential link between nanoflares and solar wind acceleration extends the importance of these small-scale events beyond just thermal balance, suggesting they may be integral to the mechanics of the Sun's mass and energy outflow. The challenge remains in capturing sufficient resolution, both in time and space, to resolve these elusive events. Advances in solar instrumentation, such as the Solar Orbiter and DKS Daniel K. Inge Solar Telescope, are closing the gap. With higher cadence and finer resolution, these missions will allow a deeper search for nanoflare signatures. While it's unlikely that nanoflares account for all coronal heating, their ubiquity in models and growing body of indirect evidence strongly supports their role. Understanding how much they contribute will help refine our global energy models of the Sun and could potentially reveal universal mechanisms that apply to other stars as well. The implications of these findings stretch far beyond solar physics. The processes behind nanoflares may be occurring in the coronas of other stars throughout the galaxy, where magnetic reconnection at small scales could dominate energy transport. The Sun, in this context, becomes a nearby test case for processes that shape astrophysical plasmas more broadly. While the definitive detection of a single nanoflare remains elusive, the mounting circumstantial evidence and the refinement of observational techniques give us hope that one day we will conclusively observe these tiny events. The search for the invisible stove that fuels the Sun's outer atmosphere continues. In many ways, nanoflares represent a compelling, though still partially hidden, answer to one of the greatest mysteries of solar physics. They exemplify the idea that countless tiny events, each imperceptible on its own, could together power the extreme environment of the sun's outer layers. Their elusive nature makes them challenging to study, but their potential contribution to coronal heating, solar wind acceleration, and solar atmospheric dynamics is undeniable. As technology advances and our understanding deepens, nanoflares may ultimately provide the key to unlocking the mysteries of the sun's behavior. Spicules are narrow, high-speed jets of solar plasma that constantly erupt across the sun's surface, shooting upward at impressive speeds. These slender structures, though only a few hundred kilometers wide, can reach altitudes of tens of thousands of kilometers. Despite their short lifespan lasting just a few minutes, the sheer number of spicules makes them significant contributors to the sun's mass and energy budget. At any given time, millions of spicules are active, forming a dense forest of dynamic motion across the sun's surface. These spicules originate from the chromosphere, the layer just above the photosphere, and extend upward into the lower corona. The speeds at which they rise typically range from 20 to 100 kilometers per s, though some can exceed 150 kilometers per s. For decades, spicules were considered intriguing but largely inconsequential phenomena. Early solar telescopes lacked the resolution to capture their structure in detail, leaving their true significance a mystery. However, modern instruments have now provided much clearer observations, revealing that spicules play a crucial role in both coronal heating and the formation of the solar wind. There are two main types of spicules, classified based on their dynamics and the evolution of their temperature. Type I spicules follow a parabolic path, rising and falling symmetrically. In contrast, Type II spicules are faster and shorter-lived, fading away without returning. These Type II spicules likely heat rapidly to coronal temperatures before merging with the solar atmosphere. Recent observations from advanced solar missions such as the Hinode satellite and the IRIS mission have dramatically changed our understanding of spicules. These studies have shown that spicules are capable of carrying both mass and energy into the corona, feeding the material that sustains solar wind streams. Additionally, their motion induces waves and turbulence in the magnetic field lines above them. Spicules are often found in regions with strong magnetic activity, and their formation seems to be tied to either magnetic reconnection at small scales or wave interactions in the lower layers of the sun's atmosphere. Although the precise trigger for spicule formation remains debated, the correlation with magnetic network boundaries is well established. Spicules can be observed in spectral lines like HALTA and CAMA-T, through where their vertical structure and evolution are most clearly seen. High-cadence imaging has revealed that spicules heat rapidly as they rise, with some reaching coronal temperatures within seconds. This transition from cooler to hotter temperatures during their ascent is a key indication of intense energy deposition during their brief rise. Though individually faint, the cumulative mass flow from spicules may rival that of the solar wind. Estimates suggest that they transport enough material to continually replenish the corona. If a fraction of these spicules heat to coronal temperatures, they could make a significant contribution to the sun's overall energy balance. Spicules are also believed to play a role in generating Alfvén waves. As they rise and twist, they disturb magnetic field lines, launching waves into the corona. These waves may dissipate their energy into the surrounding plasma, further aiding in the heating of the corona, a process that complements the nanoflare mechanism. Simulations of spicule dynamics require high-resolution magnetohydrodynamic modeling, taking into account factors such as partial ionization effects and radiative transfer, to more accurately capture the behavior of these features. Recently, models have begun to more closely match observed properties of spicules, supporting their role in upper atmospheric dynamics. Spicules are not uniform across the entire sun. They exhibit regional variation, being more intense and frequent near active regions and more uniform in coronal holes. This pattern correlates with differences in solar wind speed and composition, linking spicule activity with the overall structure of the heliosphere. Though spicules operate on a granular scale, their interactions with larger solar processes such as the solar wind make them a fundamental component of the sun's atmospheric dynamics. They demonstrate how small-scale phenomena on the solar surface can influence global processes within the sun's atmosphere. The role of spicules in solar dynamics goes far beyond their surface activity. They provide valuable insight into the physical processes occurring deep within the sun's interior. Understanding the mechanisms behind spicule formation, motion, and energy transfer is crucial for understanding the sun's complex behavior and its wider influence on space weather. As our observational techniques improve, spicules are becoming an increasingly important subject in solar research, revealing not just a solar curiosity but a key feature in the sun's inner workings. Spicules are fleeting, high-speed jets of solar plasma that erupt continuously across the sun's surface. These slender columns, though just a few hundred kilometers wide, can stretch tens of thousands of kilometers high and last only a few minutes. Before modern instruments with high observation capabilities, these quick events were nearly impossible to detect. Their discovery underscores the importance of monitoring transient, small-scale solar phenomena. Interestingly, coronal rain, a similar phenomenon, has been observed on other stars, suggesting that the underlying process might not be unique to the Sun. It could be a common feature of magnetically confined plasma in stars, occurring when the plasma reaches a thermally unstable state. Coronal rain, in essence, serves as the solar atmosphere's method of rebalancing itself. It cools, condenses, and recycles plasma in a way that's governed by the Sun's magnetic architecture, a quiet, gravitational counterpart to the Sun's more dramatic, explosive events. From Earth, coronal rain might seem like a brief and transient occurrence, but in those brief arcs of falling plasma, we find crucial insights into the limits of coronal heating and the mechanisms that both fuel and regulate the Sun's fiery outer layers. This phenomenon reveals how the Sun's atmosphere manages its temperature and energy, highlighting the complexities of solar dynamics. Another intriguing aspect of the corona is its unusual chemical composition, which deviates from what we might expect. When comparing the corona's elemental makeup to that of the photosphere, certain elements, particularly those with a low first ionization potential Phi-P, such as iron, magnesium, and silicon, are found to be significantly enriched in the corona. In contrast, elements with a high He-P, like oxygen and neon, are less abundant. This phenomenon is known as the He-P effect and has baffled scientists for decades. The difference isn't small. Elements with low Phi-P values can be enriched by factors of 3 to 4 times compared to their abundance in the photosphere. The Fi-P effect is present across various regions of the corona, including both active and quiet areas, although the intensity of the effect can vary depending on solar conditions. To understand why this occurs, we need to explore plasma physics and ion transport. Phi-P refers to the energy needed to remove an atom's first electron. Low Fi-P elements are more easily ionized in the chromosphere, the layer just above the photosphere. This ability to ionize more readily may be central to how elements are sorted in the Sun's atmosphere. One theory suggests that this separation happens in regions where both ionized and neutral atoms coexist. In these areas, electromagnetic waves and forces can act selectively on ions, mainly low Fi-P elements, while neutral atoms remain unaffected. This process leads to the preferential upward transport of low Fi-P ions into the corona. A key factor in this sorting may be Alpsven waves, which travel along magnetic field lines. These waves could transfer momentum to ions through a process called the ponderomotive force, which accelerates certain ions more effectively than others, leading to the enrichment of specific elements in the upper layers of the Sun's atmosphere. Interestingly, the FAP effect isn't consistent across the entire Sun. In coronal holes where magnetic field lines open directly into space, the FAP effect is weaker or even absent. This suggests that the Sun's magnetic field geometry and the type of heating happening in different regions play a significant role in how elements are transported and sorted in the corona. To measure the abundances of different elements, high-resolution spectroscopy is required. Instruments like the EIS, EUV imaging spectrometer aboard the Hinode satellite, and the CES, spectral imaging of the coronal environment instrument on the solar orbiter, are able to analyze emission lines from highly ionized species, which act as unique signatures for specific elements. This data helps quantify the abundance of these elements in various layers of the solar atmosphere. The Fi-P effect also shows sensitivity to the solar cycle. During periods of higher solar activity, the Fi-P-related enrichment is more pronounced, suggesting that dynamic events like flares and eruptions amplify the separation of elements during their transport into the corona. In some stars, however, a reverse FIP effect has been observed, where high FIP elements appear enriched instead. This suggests that the wave environments and magnetic conditions in these stars differ, making the FIP effect a phenomenon shaped by each star's unique conditions. Understanding this complex chemical sorting is important for space weather forecasting, because the composition of the solar wind depends on whether it originates from coronal holes or more active regions of the Sun. By analyzing elemental ratios, scientists can identify where the solar particles come from and how they move through the heliosphere. This chemical sorting challenges the simplistic view of the corona as merely an extension of the photosphere. Instead, it acts as a selective filter, a dynamic zone where wave-particle interactions and magnetic field structures determine how elements are transported. Researchers are continuously refining models to better simulate ion acceleration and the fractionation of elements in the solar transition region and corona. These efforts include using solar wind samples, X-ray spectroscopy, and real-time measurements from missions like AC and Solar Orbiter. While there has been significant progress, no single model yet fully explains the variability of the FIP effect. The relationship between waves, plasma conditions, magnetic field geometry, and atmospheric layering is intricate and remains one of the major open questions in heliophysics. Understanding the FIP effect will not only enhance our knowledge of solar chemistry, but will also improve our understanding of how stars distribute elements in their outer atmospheres. It's a unique chemical fingerprint that is shaped not just by temperature but by the electromagnetic environment and the thresholds for ionization. Ultimately, the strange chemistry of the solar corona serves a reminder that even familiar elements can behave unpredictably when subjected to the Sun's extreme magnetic conditions. While we can't directly see the far side of the Sun, thanks to a technique called heliosismology, we can listen to it. Just as sonar is used to map the seafloor, heliosismology uses sound waves traveling through the Sun's interior to infer structures hidden on the far side. These sound-like oscillations are caused by turbulent convection near the Sun's surface and travel through the solar interior, refracting and bouncing depending on local conditions. By studying how these waves travel and re-emerge, scientists can reconstruct maps of active regions, such as sunspot groups, even before they rotate into view. This technique relies on detecting subtle timing differences in how the waves move. Active regions, being magnetically and thermally different, affect how the waves propagate, creating detectable timing anomalies. To study these waves, instruments like the Helioseismic and Magnetic Imager (HMI) aboard the Solar Dynamics Observatory (SDO) provide continuous Doppler images of the Sun's surface. These images are then processed to create detailed maps of the Sun's internal and far-side structures. While the resolution of these reconstructions isn't as high as direct images, they are surprisingly accurate and useful for predicting solar activity. By knowing the location of sunspot groups that are not yet visible, scientists can predict solar flares and coronal mass ejections (CMEs) before they happen, offering valuable lead time for space weather forecasting. Heliosismology also offers the ability to track long-lived active regions as they rotate in and out of view. Some active zones last across multiple solar rotations, and their reappearance can be predicted using helioseismic data. This ability extends the forecasting horizon well beyond what imaging alone can offer. The far-side maps created through this method are updated daily and provide detailed indicators of magnetic strength and activity trends. These insights are invaluable for operational models used by space agencies, helping them assess potential risks to satellites, power grids, and astronauts from solar activity. Beyond just imaging the far side, heliosismology also allows for the mapping of subsurface flows, such as meridional circulation and zonal flows. These measurements assist in modeling the solar dynamo, providing a deeper understanding of the large-scale patterns that govern sunspot formation and the solar cycle. Similar to seismology on Earth, heliosismology interprets how acoustic waves caused by turbulent convection near the Sun's surface reflect and refract within the Sun. These waves are influenced by gravity and pressure gradients, offering a unique acoustic probe of the Sun's interior. Through this technique, scientists have detected the presence of giant Rossby waves and internal shear layers, revealing that the Sun's interior is highly structured, with dynamic patterns that influence its surface behavior over the span of months and years. Heliosismology has proven crucial in validating models of stellar structure, as the Sun is the only star we can observe in such detail. This knowledge then becomes the foundation for studying vibrations in other stars, a field known as astroseismology. As instrumentation and algorithms continue to improve, the accuracy of these far-side maps is being enhanced. Missions like the Solar Orbiter, which offers a different vantage point of the Sun, are contributing to this effort. With data fusion from multiple spacecraft, scientists expect to achieve full 360-degree coverage of the Sun, yielding even more precise maps of its far-side magnetic activity. The Sun's constant emission of charged particles, known as the solar wind, inflates a vast bubble around the solar system called the heliosphere. This protective shield helps to block out a significant portion of galactic cosmic rays, acting as a buffer for the planets. For years, scientists believed this heliosphere resembled the shape of a comet, with a rounded front and a long tail trailing behind. However, recent observations from the Interstellar Boundary Explorer, IBEX, and the Voyager spacecraft have challenged this comet-like analogy. Instead, some new models suggest the heliosphere has a more complex croissant-like shape, with lobes that are shaped not only by the solar wind, but also by the interstellar magnetic field. This revised model alters our understanding of the Sun's interaction with its galactic environment. Voyager 1 and Voyager 2, having crossed the heliopause, the boundary between solar and interstellar space at different angles and distances, have provided data that indicate the heliosphere is not symmetrical. This contradicts earlier models, which predicted a neat, elongated tail. The heliosphere's shape is determined by a delicate balance of forces: the outward pressure of the solar wind, the inward push of the local interstellar medium, and the influence of the galactic magnetic field. These factors work together to create a dynamic, ever-changing boundary that extends far beyond Pluto. IBEX, using its instruments to map energetic neutral atoms, ENAs, has provided indirect clues about the shape and density of the heliospheric boundary. These ENAs form when solar wind particles collide with interstellar atoms. Incredibly, IBEX revealed a bright ribbon of emissions that no existing model had predicted, suggesting that the boundary is aligned with the interstellar magnetic field rather than simply creating a bow shock. This discovery has forced scientists to reconsider their long-standing assumptions about the Sun's outermost frontier, emphasizing that magnetic geometry, rather than plasma pressure alone, shapes the heliosphere's contours. The new Croissant model posits that solar wind jets escape the Sun along its poles and curve back, forming twin lobes rather than a continuous tail. The heliosphere, according to this model, is more compact and pressure-balanced, with only short extensions along the Sun's equator. This shape is dictated more by magnetic forces than by the solar wind's motion. Understanding the heliosphere's shape is crucial because it affects how much cosmic radiation enters the inner solar system. Its geometry also influences which regions of space are more exposed during different phases of the solar cycle, and it plays a role in the movement of cosmic rays and interstellar dust. The outer edge of the heliosphere, called the heliopause, is not a static boundary. It expands and contracts in response to the Sun's activity, growing during periods of strong solar wind and shrinking during quieter times. This breathing motion adds further complexity to the structure and function of the heliosphere. NASA's upcoming Interstellar Mapping and Acceleration Probe, IMAP, aims to deepen our understanding of this region. IMAP will provide high-resolution ENA mapping, which will help clarify how solar and interstellar forces interact. This mission may either confirm or challenge the Croissant model with greater precision, offering a clearer picture of the heliosphere's true shape. The shape of the heliosphere is not only essential for understanding space weather here on Earth, but it also impacts our interpretation of data from interstellar probes. For example, the Voyager spacecraft's measurements must be adjusted based on local heliospheric geometry. This is crucial because knowing where each probe crossed the boundary helps scientists put their measurements in context. Understanding the heliosphere's shape is vital for interpreting data from missions that probe the outermost reaches of the solar system. Beyond Earth, the heliosphere's structure has implications for planets like Uranus and Neptune, where the changing shielding conditions depend on their position relative to the heliosphere's shape. The varying exposure to cosmic rays, influenced by the heliosphere's asymmetry, can affect space weather even in the far reaches of the solar system. The heliosphere is, in essence, the sun's fingerprint on the galaxy, a vast magnetized bubble that marks the limits of the sun's influence. As the sun moves through the Milky Way, this bubble interacts with different interstellar environments, gradually changing shape and properties over time. By studying the heliosphere's form, scientists gain valuable insight into how stars interact with their environments, and they can apply this knowledge to better understand the stellar wind bubbles around other stars throughout the galaxy. The sun's heliosphere serves as one example among billions, offering a unique perspective on how stars in different parts of the galaxy protect their planetary systems. When it comes to forecasting space weather, coronal mass ejections (CMEs) play a significant role. CMEs are huge bursts of plasma and magnetic fields ejected from the sun's corona. These eruptions can trigger geomagnetic storms that disrupt satellites, power grids, and communications here on Earth. However, not all CMEs are equally dangerous. The key factor that determines their potential for harm is the magnetic orientation of the cloud when it reaches Earth. If the CME's magnetic field is aligned northward, it tends to pass by Earth's magnetic field with little interaction. But if it's southward, it can merge with Earth's magnetosphere, injecting energy into the system and potentially causing auroras or even blackouts depending on its strength. The challenge in forecasting the magnetic orientation of a CME before it reaches Earth is one of the biggest hurdles in space weather science. Current methods rely on tracking the CME's speed, size, and direction using coronagraphs and heliospheric imagers, but the internal magnetic structure of a CME is largely unknown until it impacts Earth. This is because CMEs twist and change as they travel through space. The magnetic field configuration that leaves the Sun may not match what arrives at Earth. Some missions attempt to predict the CME's magnetic structure based on its source region, using magnetograms to estimate the polarity of the flux rope. However, these predictions are still uncertain, especially if the CME undergoes significant changes during its journey. The STEREO and ASOHO missions have significantly enhanced our ability to observe coronal mass ejections (CMEs) in 3D, giving us clearer insights into their shape and movement. However, despite these advancements, we still face challenges in predicting the internal magnetic fields of CMEs. Since we can't directly measure these fields, our models have to make assumptions about the behavior of flux ropes, which limits the precision of forecasts, particularly when it comes to predicting their magnetic orientation. NASA's upcoming Solar Sea EOVST mission, along with instruments aboard Solar Orbiter, could provide us with new ways to study the formation of CMEs, including possible early signs of magnetic twisting. Currently, the only real-time measurements of CMEs are made by satellites like ACE or DS-GOVAR, positioned at L1, upstream from Earth. These satellites offer between 15 and 60 minutes of lead time, giving us enough time for short-term responses, but not enough to protect broader infrastructure. The ultimate goal is to predict the CME's magnetic orientation 1 or 2 days in advance, which would allow for more proactive measures. Achieving this requires improving our models of CME initiation, especially regarding the structure and twist of flux ropes during the launch phase. By combining these models with solar surface observations and magnetic field extrapolations, we could gain more reliable predictions, though there are still many uncertainties. Some scientists suggest that placing a network of satellites between the Sun and Earth could help gather early magnetic profiles of incoming CMEs. These space weather sentinels could take multiple measurements of the magnetic fields, providing better forecasts for CME orientation. Until these systems are developed, we rely on statistical methods. For example, CMEs originating from specific solar quadrants are more likely to rotate southward as they travel. By combining this with source magnetograms and flare orientations, we can make probabilistic predictions, though not exact forecasts. The impact of CME magnetic orientation is far-reaching. It affects much more than just power grids. It also influences radiation exposure for high-latitude flights and astronauts, the risk of satellite collisions, and the efficiency of radio communications. In some cases, it's the difference between a minor disruption and a catastrophic event. Auroras are one of the most visible results of magnetic reconnection between Earth and southward CMEs, but there are many other less obvious consequences. For instance, pipelines can experience dangerous electrical surges, GPS signals can be disrupted, and the expansion of Earth's atmosphere increases the risk of satellite collisions. All these impacts depend on the orientation of the CME's magnetic field when it arrives. Accurately predicting this orientation could revolutionize space weather forecasting, drastically improving how we prepare for solar storms and minimizing their impact on our technology. Until then, the research continues, both on the ground and in space. The day we can not only predict when a CME will hit, but also know exactly how its magnetic field will interact with Earth's will mark a major milestone in our understanding of the Sun-Earth connection. Similar patterns have been observed during past solar minima, such as the Spora minimum from 1460 to 1550 and the Dalton minimum from 1790 to 1830. These periods of solar inactivity show us that the Sun's magnetic activity can fluctuate over centuries. While solar activity is generally predictable, it's also influenced by random and possibly chaotic processes deep within the Sun. This suggests that grand minima aren't rare anomalies, but rather they're a natural part of solar behavior. Models of the solar dynamo, our understanding of how the Sun generates its magnetic field, now include factors like magnetic memory, random fluctuations, and flow instabilities. These can trigger phases of weak or absent solar cycles, akin to grand minima. Still, predicting when these periods will occur remains a mystery. During a grand minimum, the heliosphere, or the bubble of solar wind surrounding the Sun, contracts slightly, which reduces the protection from cosmic rays. This allows more galactic cosmic rays to reach Earth, affecting the planet's atmosphere and increasing radiation levels. Interestingly, a quieter Sun allows more cosmic radiation to reach us, highlighting that space weather isn't just driven by solar activity, it's an ongoing phenomenon. While we don't have data from the Maunder minimum, which occurred long before the age of satellites and modern electronics, we can imagine that increased cosmic ray flux could pose risks to satellites, electronics, and human health, particularly in space. Some scientists worry that a future grand minimum could coincide with or even exacerbate the effects of climate change caused by human activity. However, even the most intense grand minima would likely only result in modest global cooling. This wouldn't be enough to reverse the current warming trend, but could still play a role in regional climate changes. The Sun has since recovered from the Maunder minimum and returned to its regular 11-year cycle of activity, though the potential for future minima remains. By studying solar polar fields, sunspot trends, and the flow of materials inside the Sun, we may find clues to future grand minima, but predicting them is still beyond our reach. The Maunder minimum serves as a reminder that the Sun is far from a reliable metronome. Its rhythm is complex, capable of deep pauses and shifts. These pauses have left their mark on Earth's climate, history, and civilization, subtly highlighting our dependence on the Sun's consistency. Studying these quiet phases helps us better understand solar variability and the sensitivity of Earth's systems to even slight changes in solar behavior. The Sun doesn't need to be loud to have an impact. While our Sun seems relatively calm compared to some of its stellar cousins, recent observations from space telescopes like Kepler and TESS have revealed that stars similar to the Sun, called solar twins, can produce massive eruptions known as superflares. These superflares can release hundreds to thousands of times more energy than the largest solar flares we've recorded. It raises a key question. If stars like the Sun can produce such violent outbursts, why hasn't our Sun done the same? Or perhaps it has, and we simply haven't observed it during modern times. Researchers suggest that superflares are more common in younger, faster rotating stars. Faster rotation boosts the magnetic dynamo process, which generates magnetic fields and increases the activity of the star's outer atmosphere. This could explain why some stars show frequent superflares while the Sun doesn't. However, some superflares have been recorded on stars with similar rotation periods and characteristics to our Sun, which blurs the line between active and inactive stars and challenges the assumption that the Sun is fundamentally different. It's possible that our Sun is simply in a calm phase right now. If our Sun were to emit a superflare, the consequences could be disastrous. Modern infrastructure, satellites, power grids, and communication systems could suffer severe damage. The Carrington event of 1859, a major solar storm, is often cited as an example of the potential dangers, but even that event would be dwarfed by the magnitude of a true superflare. Evidence from tree ring records and ice cores, particularly from the so-called Miyake events, suggests that the Sun has produced much larger solar outbursts in the past, leaving behind chemical traces like increased carbon-14 levels. These signatures point to the possibility of extreme solar activity in pre-industrial times, long before we had the technology to track it. Despite the Sun's relatively calm behavior today, these records imply that it might not be immune to superflares. Understanding what triggers superflares in solar twins is crucial for preparing for the potential risk to modern technology. The relationship between magnetic field strength, complexity, and the star's rotation rate seems to be key. Some models suggest that tightly braided magnetic loops in the star's atmosphere could store massive amounts of energy, which is released during a superflare. Another indicator is the presence of large, persistent star spots, which are common on stars that produce superflares. These giant spots can cover up to 10% of a star's surface and are thought to anchor the energy buildup necessary for a superflare. Observations of these stars during flares show high energy emissions in ultraviolet, optical, and X-ray wavelengths, with rapid rises and slower decays in the light curves similar to solar flares but on a much larger scale. This research isn't just theoretical. As we plan long-term space missions and continue to rely on satellite networks, understanding the limits of solar behavior becomes crucial for risk assessment. If the Sun can produce a super flare, even a modest one, our preparedness will be key. Space missions like Solar Orbiter and ground-based observatories like DKEST are now providing high-resolution data that may help us identify early warning signs of unusual solar activity. For now, the Sun remains within the bounds of what we consider normal. But the solar dynamo which drives the Sun's magnetic field is inherently chaotic. Just because we haven't seen a superflare in recent centuries doesn't mean it's impossible. Observations of solar twins keep the possibility open. Understanding these superflares also helps us gauge what to expect from stars at different stages of their evolution. The Sun may be in a quiet phase now, but it's important to remember that this calm state isn't necessarily permanent. The study of superflares on solar twins helps us understand the potential extremes of stellar magnetism, forcing us to reconsider what is typical, what is exceptional, and what risks might be hidden beneath the calm surface of our star. A sunquake may indicate that a region of the Sun has released its built-up magnetic energy, or it could signal that more is yet to come. The pattern of these waves, how they spread, their symmetry, and how fast they move, provides important clues about the Sun's outer layers. Think of it as an acoustic snapshot of the Sun's surface, complementing deeper studies of its interior using helioseismology. Thanks to advancements in technology, we're detecting more sunquakes than ever before. Their small size means they're often overlooked unless we have high-resolution data with precise timing. Missions like the Solar Orbiter will soon provide new angles to catch these fleeting seismic events, offering fresh insights into solar activity. In the world of stellar physics, sunquakes are the echoes of solar eruptions. They are short, powerful signals that reveal the magnetic stresses building up and suddenly releasing on the Sun's surface. Unlike earthquakes on Earth, sunquakes occur in a star with no solid crust. They're born through the Sun's plasma. Solar tsunamis, another phenomenon observed in the 1990s by SOHO, are massive plasma waves that race across the Sun's surface following major eruptions. These waves can travel at speeds of hundreds of thousands of kilometers per hour, expanding like shock waves. Despite their name, solar tsunamis aren't related to ocean waves. They are magneto-hydrodynamic waves, also known as EIT waves. Initially considered rare, solar tsunamis are now known to occur much more frequently, often in conjunction with large flares and CMEs. These waves spread across the Sun's corona and can sometimes cover the entire solar disk in just minutes. But they are no gentle ripples. Solar tsunamis compress, heat, and disturb everything in their path. As they travel, they can trigger oscillations in coronal loops, rearrange magnetic field lines, and even spark secondary eruptions. Their energy and momentum reveal major changes occurring in the Sun's atmosphere. Solar tsunamis are often linked to the birth of CMEs. As a CME lifts off, it pushes against the surrounding magnetic environment, sending a shock wave ahead of it. This pushes plasma and magnetic fields outward, creating a stellar bow shock. By studying these waves, scientists can estimate the energy of the CME. Typically, these waves appear as bright arcs in extreme ultraviolet EUV wavelengths. Behind them, we sometimes see coronal dimming, a region where plasma has been evacuated. The speed and direction of the wave provide valuable clues about the magnetic field structure and plasma density of the Sun's corona. Not all solar tsunamis are the same. Some are faster magneto-hydrodynamic waves, true physical compressions. Others are pseudo-waves created by the restructuring of magnetic fields rather than pressure-driven propagation. Identifying the difference requires high-frequency, multi-wavelength data. The fastest solar tsunamis can travel over 1,000 kilometers per cs and are associated with highly energetic flares and CMEs, often signaling intense space weather events. Even slower tsunamis still carry important information about local conditions within the corona. By tracking the wave's behavior across different solar regions, scientists can map properties like magnetic field strength, plasma temperature, and density gradients. Solar tsunamis act as real-time diagnostic tools, allowing us to probe the Sun's outer layers. Some solar tsunamis even trigger secondary eruptions or brighten distant regions, suggesting that magnetic stress and energy can propagate across vast areas of the Sun. The solar surface isn't isolated. It's a highly interconnected, dynamic system. By using multiple observations, such as those from the stereo mission, scientists can build 3D models of these waves, showing their height, curvature, and interactions with solar structures. Understanding their geometry helps improve CME forecasting and flare diagnostics. While solar tsunamis are not a direct threat to Earth, they play an important role in predicting CMEs and flares. Real-time detection of these waves is crucial for space weather monitoring. Tools using machine learning are being trained to automatically spot these wavefronts in solar data streams. Such automated systems could significantly improve the speed of space weather alerts, especially when combined with tracking CMEs and analyzing flares. The study of solar tsunamis blends several fields of physics, from plasma dynamics to magneto-hydrodynamics and solar behavior. They show us how a single flare, or CME, can ripple across the entire Sun, releasing massive amounts of energy. As our imaging technology improves, we'll likely uncover even more details within these waves. Beneath their sweeping arcs, we may discover localized compressions, shocks, and current sheets, adding new layers to our understanding of solar activity. The story of solar tsunamis is just the surface. Below lies a deeper tale in solar physics. Flux ropes are tightly wound bundles of magnetic field lines that coil like springs within the Sun's atmosphere. These ropes store massive amounts of magnetic energy, and when they destabilize, they can lead to powerful solar eruptions like flares and CMEs. Flux ropes are essential to understanding solar magnetism. They form when magnetic loops twist due to differential rotation, shearing motions, or emerging magnetic flux. As the twist accumulates, the structure becomes more helical. When the magnetic tension reaches a breaking point, the rope can erupt, releasing a huge burst of energy. Sometimes, flux ropes stay stable for hours or even days before erupting, allowing scientists to study them in detail. Instruments like SDO's AIA and Hinode's XRT capture these ropes in the corona, often showing up as dark filaments or glowing arches hovering above the surface. Before a flux rope erupts, it often forms a sigmoid, a characteristic S-shape visible in X-rays or EUV light. This shape signals a twisted and sheared magnetic field, which is ready to release its energy. When the rope erupts, it can power both a flare and a CME simultaneously. Magnetic reconnection plays a key role in this process. As the flux rope rises, it stretches the surrounding magnetic field. Eventually, the field lines snap and reconnect beneath the rope, forming flare loops and sending the rope soaring upwards. This is the typical CHKP eruption model. Sometimes the twist within a flux rope is preserved even in CMEs. Coronagraphs and in situ detectors have captured magnetic clouds in space that match the expected helical shapes of flux ropes. The degree of twist or helicity in a flux rope affects its stability. If the twist is too weak, the rope may collapse, but if it's too strong, the rope becomes unstable and may break apart, leading to a CME. The dynamics of these flux ropes are governed by fundamental plasma physics, making them a universal structure across different scales from the Sun's surface to planetary magnetospheres, laboratory plasmas, and even astrophysical jets. The study of flux ropes helps us predict solar eruptions. By monitoring the twist and shearing motions in these structures, scientists can assess the likelihood of an eruption. Automated algorithms are already analyzing solar magnetogram data to track indicators of flux ropes, improving flare and CME predictions. Some theories suggest that flux ropes may even form beneath the photosphere before becoming visible. This process could leave detectable signatures, which might be captured by helioseismology or subsurface modeling. Solar filaments are often the surface manifestations of flux ropes, visible from the side. These cool, dense structures hover in the corona, held in place by magnetic tension. When they erupt, the internal helicity of the flux rope is revealed, traced by plasma motion and filament rotation. The alignment of a flux rope's magnetic axis and direction can determine its impact on Earth. If a CME carrying a southward-aligned flux rope strikes Earth, it can enhance magnetic reconnection, increasing the likelihood of geomagnetic storms and auroral activity. The shape of coronal loops reveals the hidden structure of the Sun's magnetic field, transforming an abstract idea into something we can observe and measure. These loops connect regions on the solar surface where magnetic fields of opposite polarity meet. When these magnetic fields rearrange, whether due to flares or flux surges, the resulting loops are a direct consequence of the energetic adjustments occurring. Each loop serves as a visible imprint of the Sun's magnetic dynamics in action. Thanks to extreme ultraviolet EUV images from instruments like SDO, these arcs are captured in stunning detail, showing variations in temperature, density, and cooling time across their lengths. Loops can range from short-lived small structures to enormous arcs that persist for hours or even days. In active regions, they often overlap, forming complex plasma forests that stretch tens of thousands of kilometers high. These loops map out the topography of solar magnetism. The appearance and brightness of these loops allow us to infer key physical processes like thermal conduction, radiation, and mass circulation. Magnetohydrodynamic models aim to simulate their behavior, but doing so is a complex challenge. The Sun's geometry, turbulence, and the range of timescales from seconds to days add layers of difficulty. When loops are heated by phenomena like nanoflares or magnetic waves, they shine brightly in specific UV bands, offering a spectroscopic window into the energy states and composition of the plasma within. Over time, these loops can expand, oscillate, or collapse, reflecting changes in the magnetic fields that sustain them. For example, transverse oscillations help scientists estimate plasma density and magnetic field strength. Every movement within a loop provides clues about internal conditions. The geometry of the loops also affects how energy is transported. Heat generated at their base can be conducted upwards, cooling through radiation or convection. Understanding this energy transfer is essential for solving the mystery of why the Sun's corona is hotter than its surface. Giant loops, particularly those that form after large flares, can create long, stable arcs with cooled plasma collecting in the lower parts. Sometimes, gravity causes this plasma to fall back down, creating a phenomenon known as coronal rain. The structure of these loops allows us to map regions of magnetic stress. In areas where many loops intertwine, the likelihood of explosive reconnections increases. Loops, therefore, are not only consequences of magnetic activity, they can also be precursors to solar eruptions. Whether small or large, these structures follow the same fundamental laws of confined plasma physics. This allows us to use the Sun as a laboratory for understanding similar phenomena in stars and Earth's magnetic environment. Advanced simulations have improved our ability to replicate the behavior of these loops, including effects like dissipation, instabilities, and plasma feedback. However, modeling all the scales involved, especially when loops interact with waves or jets, remains a challenge. Statistical studies of loops also show patterns that help us understand how active regions evolve and their role in maintaining the corona's energy balance. Loops, in essence, are temporary sculptures shaped by solar magnetism. By measuring their shape, temperature, and evolution, we can observe the magnetic field's imprint on the plasma. Coronal mass ejections, CMEs, are among the Sun's most powerful outbursts. During a CME, billions of tons of plasma are launched into space at speeds exceeding 1,000,000 kilometers per hour. In terms of mass, a CME is equivalent to hurling a mountain the size of Everest into space. These eruptions occur when large magnetic structures like flux ropes become unstable and collapse, releasing the stored energy in the twisted fields. This explosion sends ionized plasma beyond the sun's corona and often into the inner heliosphere. The size and speed of a CME determine its potential impact. When directed toward Earth, a CME can interact with our planet's magnetic field, causing geomagnetic storms. The magnetic orientation of the CME, especially if it carries a southward-facing field, plays a major role in the severity of these effects. Coronagraphs on missions like SOHO and STEREO capture the CME as a bright bubble expanding rapidly after the eruption. The so-called halo effect often signals that the CME is heading toward Earth. Although CMEs are typically associated with flares, not all of them are preceded by one. In some cases, a magnetic instability builds up slowly and reaches a critical point, causing a CME to erupt without any significant radiation emission. The expelled plasma contains protons, electrons, and nuclei of elements like helium and iron, all held together by a magnetic field. As the CME travels, this structure interacts with the solar wind and can accelerate additional particles. Satellites in orbit and ground-based detectors monitor the magnetic field and plasma density in real time. Early detection allows scientists to estimate the intensity of the impending storm. A CME's impact can last for hours or even days. In addition to generating powerful auroras, it can overload power grids, disrupt satellite operations, and interfere with communication systems. Extreme events like the Carrington event of 1859 demonstrated the destructive potential of these solar ejections. Predicting the trajectory and rotation of a CME remains difficult. The cloud can deform, expand unevenly, or be deflected by areas of intense magnetic fields, making its magnetic orientation at Earth's arrival challenging to predict. Missions like the Parker Solar Probe and Solar Orbiter are helping to refine our understanding of how CMEs form and evolve as they travel through the sun's inner regions. By measuring the magnetic fields and plasma density in these regions, we can improve our ability to predict and assess risk from these space weather events. CMEs don't happen in isolation. During periods of solar maximum, multiple CMEs can erupt per day, sometimes one after the other. One CME can even pave the way for subsequent eruptions, amplifying their effects or altering their path. While most of the material in a CME escapes the sun, some of it can recirculate and return as coronal rain. This return flow provides valuable information about the geometry of the ejection and the forces at play during the event. CMEs also serve as a bridge between the sun and the interstellar medium, carrying magnetic fields, matter, and angular momentum. These ejections help shape the heliosphere and can influence the environments of other stars as well. In terms of energy, a single CME can release the equivalent of billions of nuclear bombs. Yet this process happens regularly on our sun, often invisible to the naked eye. It's a reminder of the immense scale at which the sun operates. The Carrington event of 1859 is still the benchmark for solar storms. In September of that year, the sun unleashed a flare so intense that it remains the reference point for extreme space weather. The event was first observed by Richard Carrington, who saw a sudden brightening on the solar disk while monitoring sunspots. Just hours later, Earth felt the effects. The flare was accompanied by a massive CME that traveled from the sun to Earth in a record-breaking 17.6 hours. Upon reaching Earth, the CME compressed our planet's magnetosphere and induced electric currents in the ground, creating geomagnetic chaos. Auroras were seen as far south as the Caribbean, and in places like Havana and Rome, the skies glowed with bright red and green hues. In some regions, people thought the sky was on fire, while miners in Colorado even mistook it for dawn and started preparing breakfast. Telegraph systems worldwide malfunctioned, operators were shocked, equipment sparked, and some systems continued to operate even when disconnected from power. The wires acted like antennas, absorbing geomagnetically induced currents that overwhelmed the early technology of the time. Despite the limited technological infrastructure of the 19th century, the event was a stark reminder of the sun's immense power and its capacity to disrupt life on Earth. If a Carrington-class event were to happen today, it could bring the world's electrical grids, satellite networks, aviation, and digital infrastructure to a standstill. Experts estimate that the damage could reach into the trillions of dollars. Power transformers, particularly in high-latitude areas, are especially vulnerable to geomagnetically induced currents GMEs. Blackouts could last weeks, and recovery would be both costly and complicated. In addition to the damage to electrical infrastructure, such an event would also lead to a significant ground-level enhancement, GLE, in cosmic rays, a rare phenomenon that raises radiation levels at flight altitudes. This increased radiation would pose risks to both biological tissue and sensitive electronics, making GLEs one of the most dangerous aspects of solar storms. Tree ring and ice core data show that the Carrington event wasn't a unique occurrence, though it was certainly extreme. Similar events, such as the Miyake events, have likely occurred in the past. However, Carrington's event remains the clearest example due to the direct human observations made at the time. Carrington's original sketch of the flare and sunspots continues to be studied today, and his careful records, combined with magnetic observatory logs from across the globe, have allowed scientists to reconstruct the storm in great detail. It serves as an early case study ahead of its time. The Carrington event also sparked early interest in how solar flares might impact Earth. While scientists didn't fully understand the mechanisms behind solar activity, the clear connection between solar events and geomagnetic disturbances was undeniable. This insight laid the foundation for future research into how solar activity affects technology. Today, models use Carrington-like scenarios to prepare for worst-case space weather events. These models take into account CME speed, density, and magnetic orientation to estimate potential outcomes. Governments and space agencies rely on these models to plan for contingencies and strengthen infrastructure resilience. Modern satellites constantly monitor the sun, and early warning systems can now provide hours of lead time before a solar storm strikes. However, the ability to predict the magnetic orientation of a CME, an essential detail in determining the storm's severity, remains an unsolved challenge. In many ways, the Carrington event would still catch us off guard today. Its significance goes beyond its intensity. Its completeness is what sets it apart. The event included a flare, a CME, fast transit, visible auroras, technological impacts, and a wealth of archival data. It's the full spectrum of solar-terrestrial interaction, all in one event. On March 13, 1989, the province of Quebec, Canada, experienced a modern-day example of solar disruption when a powerful geomagnetic storm knocked out power for over 6 million people. Within just 90 seconds, a cascading failure in the Hydro-Quebec power grid plunged the entire region into darkness. The storm had been triggered by a CME several days earlier. As the shockwave reached Earth, it compressed the magnetosphere and induced powerful electric currents into the ground, particularly in areas with conductive bedrock like Quebec. These geomagnetically induced currents, GCs, overloaded the power infrastructure, and protective systems failed to respond quickly enough. A key transformer in the James Bay network tripped, setting off a chain reaction that destabilized the entire grid. The blackout lasted for 9 hours. Although it happened just before dawn, the effects were far-reaching. Subway systems stopped, businesses shut down, and communication lines were disrupted. The loss of power placed a significant strain on public services, and the harsh winter conditions in Quebec made the situation even more challenging. Beyond Quebec, satellites and power systems in the United States also recorded anomalies. Transformers in New Jersey and New England overheated. Some satellites lost their positioning, and radio communication in high-frequency bands became unreliable for hours. The storm also produced auroras visible as far south as Texas and Florida. These stunning light displays were caused by solar particles funneled along Earth's magnetic field lines, exciting oxygen and nitrogen atoms in the atmosphere. Although not as powerful as the Carrington event, the 1989 Quebec storm highlighted how even moderate solar storms could cause widespread technological disruption. It was a wake-up call for the power industry, prompting utilities to take geomagnetic risks more seriously. Following the event, power companies began monitoring space weather forecasts, installing GIC blocking systems, and developing response protocols. The blackout also underscored the vulnerability of high-latitude regions. Near the poles, Earth's magnetic field lines converge, creating pathways for solar particles and currents to reach the surface more easily. This makes northern regions more susceptible to solar storm impacts. Insurance companies and risk assessment agencies now account for solar storms in their models. The Quebec 1989 blackout demonstrated that solar activity can affect more than just satellites. It can have a serious impact on terrestrial infrastructure as well. Long transmission lines, in particular, are highly exposed. In response, space agencies like NASA and the International Space Agency (ISA) expanded their monitoring systems to provide real-time solar wind and magnetic field data. This allows operators to prepare for incoming solar storms. The Quebec event also helped raise public awareness of solar weather risks. News reports about the auroras and the blackout made space weather a topic of mainstream conversation, turning it from a niche concern to a pressing issue with real-world consequences. From a scientific standpoint, the blackout offered valuable data. Undiode magnetometers, transformer logs, and satellite telemetry all contributed to modeling how GICs flow through power grids. These models continue to evolve, helping improve forecasting and protective strategies. The blackout was a clear signal that we're increasingly dependent on systems that are vulnerable to the sun's activity. GPS, aviation, internet cables, and pipelines can all be affected by solar storms. The 1989 event was a local disruption, but it served as a global warning about the vulnerability of modern infrastructure. Commercial aviation, particularly flights over the poles, also faces unique risks from solar activity. Unlike equatorial routes, polar flights pass under open magnetic field lines, where energetic particles from solar storms can more easily enter the atmosphere. This increases the radiation risk for aircraft, crew, and passengers during space weather events. Normally, cosmic radiation levels at cruising altitudes are already higher than at sea level, but during solar proton events, the radiation dose can spike dramatically, especially over the poles. For this reason, airlines closely monitor space weather to adjust flight paths and altitudes when radiation levels are predicted to rise. In the event of a solar storm, the FAA and other aviation authorities have set radiation exposure thresholds for crew members, especially pregnant workers and frequent flyers. While a single polar flight during a storm may not pose an immediate danger, cumulative exposure is a concern over time. Beyond radiation, polar regions are also vulnerable to radio blackouts. High-frequency HF communication, which is crucial for polar operations, relies on the ionosphere, and solar flares and geomagnetic storms can severely disrupt or completely disable these frequencies. Without reliable communication, air traffic control becomes more difficult, creating safety risks. To prevent this, solar activity forecasts are incorporated into aviation planning. Several incidents, such as the 2003 Halloween storms, led airlines to reroute polar flights to lower latitudes, preventing unnecessary radiation exposure and ensuring continuous communication. Airlines now use real-time data from organizations like NASA, NOAA, and the International Space Environment Service to track solar conditions. If a major event is predicted, operators decide whether to reroute, cancel, or delay flights based on pre-established protocols. Flight altitudes also affect radiation exposure. At higher altitudes, there's less atmospheric shielding, so descending a few thousand feet can help reduce radiation exposure. This tactic is sometimes used when rerouting isn't feasible. The South Pole is particularly exposed because it lacks the geomagnetic shielding found at higher latitudes. Flights over Antarctica or near the southern auroral oval must carefully consider both radiation and communication risks, especially during the solar maximum phase. Polar routes offer fuel efficiency and shorter travel times between continents, but as solar activity fluctuates, so does the operational risk. Airlines must balance fuel savings with the safety of their passengers and crew. Severe solar storms can disrupt scientific missions and delay logistical operations. As commercial space travel and high-altitude tourism continue to grow, the relationship between aviation and space weather becomes even more crucial. Stratospheric balloon flights and suborbital journeys may experience radiation levels similar to those encountered in low Earth orbit. This emphasizes how solar physics directly impacts everyday activities. A solar flare can ripple through decisions about airline routes, flight paths, and passenger itineraries. It's space weather at work, not just in theory, but in our skies. As monitoring improves and predictive models evolve, polar flights will remain safe but better protected. Awareness, preparation, and flexibility are key to ensuring aviation's resilience against the unpredictable influence of the sun. When astronauts venture into space, Earth's magnetic field no longer provides protection against solar particles and cosmic rays. radiation becomes one of the most significant hazards for crews on missions beyond low Earth orbit. Shielding strategies are critical and often shape mission design and safety protocols. During solar storms, high-energy protons can intensify rapidly, and without proper shielding, astronauts could receive dangerous doses leading to radiation sickness or long-term health effects. The challenge is to provide effective shielding without adding too much mass to the spacecraft. On the International Space Station, ISS, shielding is distributed strategically with aluminum and polyethylene layers designed to block particles. During solar events, crews move to the most protected areas, like the service module or areas near water supplies, which offer additional radiation protection. Radiation exposure is cumulative, and each mission contributes to an astronaut's career radiation dose, which is monitored and regulated. Space agencies set dose limits based on factors like age, sex, and role to minimize the lifetime risk of cancer and other potential health issues. Galactic cosmic rays, GCRs, present a constant threat, even outside of solar storms. Unlike solar protons, GCRs are extremely high-energy particles that are harder to shield. Materials used to block them often produce secondary particles, complicating the shielding process. Water, polyethylene, and hydrogen-rich materials are preferred for their ability to block protons without generating too many secondary particles. Future spacecraft may even use water or fuel tanks as part of their shielding system, combining structural integrity and safety. Lunar missions face additional challenges due to the absence of a magnetosphere and the thin regolith. Astronauts on the Moon will have minimal protection and must rely on quick shelter access during solar particle events. Forecasting becomes essential, as does the design of emergency shelters. Mars missions will face even greater difficulties. The journey to and from Mars, along with surface stays, exposes astronauts to prolonged radiation levels. Some proposals suggest building habitats using Martian soil or utilizing underground lava tubes to shield long-term explorers. One idea being considered is active shielding, creating artificial magnetic fields around spacecraft. While this concept is still theoretical, such systems could mimic Earth's magnetosphere by deflecting charged particles. However, power and stability requirements are major hurdles. NASA and the European Space Agency (ESA) are already testing shielding materials on the ISS, using passive dosimeters and instrumented mannequins like Matroska. These experiments track radiation exposure in different areas of the spacecraft and measure how various materials block radiation. This data is invaluable for future mission planning. As private companies enter human spaceflight, they will also need to consider radiation in spacecraft design. Shielding choices will affect not only the cost and weight of the spacecraft, but also the safety of the crew. Mission timing will also be crucial. Flights may be scheduled to avoid periods of solar maximum when solar flare and CME activity is at its highest. To monitor radiation levels, space agencies rely on real-time data. Artificial intelligence could be used to aid future radiation response. Onboard systems might detect solar conditions and recommend in-the-moment shelter strategies, ensuring quick responses when ground contact is limited or delayed. Radiation remains one of the greatest challenges for long-term space exploration. While microgravity, isolation, and logistical issues affect the body and mind, radiation silently threatens the health of astronauts, demanding constant innovation in protective technologies. As we move toward moon bases and Mars missions, shielding will determine the success and safety of these endeavors. It's not just about adding layers, it's about materials, monitoring, and mission design. In space, the sun is both beautiful and dangerous, and proper shielding makes all the difference. In solar observation, a critical region stands out. The apparent center of the solar disk. When an active region aligns with this point, it increases the likelihood that the most dangerous solar ejections will strike Earth directly. This area is often referred to as the fire zone due to its potential for producing severe solar storms. The alignment of a CME with the Sun-Earth line enhances the probability of a direct impact, raising the chances of intense geomagnetic disturbances. Active regions located near the center of the Sun are carefully monitored by space agencies, especially if they display twisted magnetic fields, flux ropes, or complex sunspot patterns. These are indicators of potential flare and CME activity. The geometry of solar positioning plays a vital role in space weather. When a CME is released from the center of the Sun, it is more likely to travel along a path that intersects with the Earth. This alignment is a critical factor in predicting the intensity of solar storms. Instruments like coronagraphs can more easily detect symmetrical CMEs when they originate from the Sun's center, making it a key region for solar surveillance. The central zone also offers a clearer view for spectroscopic measurements. Without the distortion caused by the Sun's edges, these measurements are more accurate, helping predict the behavior of solar activity. There is a narrow time window, about 3 days, during which an active region stays in this kill zone. During this period, any flare or CME becomes particularly significant for early warning systems, as the response time for Earth-based preparations is short. Probes stationed at L1, such as the Dieskov satellite, continuously monitor solar wind data from this direction. When a central region releases a CME, the measurements of magnetic field, density, and velocity allow for a more accurate prediction of its impact on Earth. Observing satellites from the STERO mission also help by providing a perspective view which can confirm if the ejection appears symmetrical or has deviated, potentially reducing the risk. This zone also serves as the basis for three-dimensional simulations of CME propagation. Data from magnetograms, helioseismology, and extreme emissions are combined to track the CME's path and its interaction with the interplanetary magnetic field in real time. The study of these solar dynamics gives us the best chance of predicting and preparing for the most dangerous solar weather events. The Sun's photosphere, the surface we see, is far from static. When viewed in high resolution, it reveals a bubbling pattern created by dynamic plasma cells known as solar granulation. Each cell is about the size of Texas and lasts only a few minutes. This motion, a result of convection, occurs as hot plasma rises from within the Sun and cools as it reaches the surface. The cooler plasma then sinks back down, continuing the cycle. This constant movement is responsible for renewing the Sun's visible surface at every moment, creating a continuous boiling effect. The bright centers of these cells indicate the rising plasma, while the darker edges represent the sinking material. This dynamic process is a direct manifestation of energy transport from the Sun's inner layers to the surface. Observations with ground-based and orbital telescopes allow us to capture this process in stunning detail, showing how the pattern shifts in seconds and revealing the turbulent nature of the solar surface. Plasma within the cells can move at speeds of up to 2 km per s, making it one of the most fascinating and energetic phenomena in the solar system. The Sun's surface is far from static. It's alive with motion. What we see as the Sun's surface is actually a bubbling, dynamic pattern called granulation. These cells, each about the size of Texas, are the result of convection within the Sun. Hot plasma rises to the surface, cools, and then sinks back down, creating this constant flow of energy. Each cell is like a tiny sound source, generating acoustic waves that reverberate through the Sun's interior. These waves are crucial in helioseismology, helping scientists map the Sun's inner layers. But granulation isn't the only type of activity on the Sun. There are also supergranulations, larger patterns stretching about 30,000 kilometers across, lasting up to 2 days. These larger structures impact how magnetic fields are distributed and play a key role in forming active regions on the Sun. By studying granulation, we gain insight into how the Sun's magnetic field is organized on its surface. The convective flows drag and concentrate magnetic field lines, helping magnetic spots and arcs to emerge. To simulate how this granulation works, scientists use three-dimensional magnetoconvection models. These models combine fluid physics, thermal transport, and magnetic interactions to help predict how the Sun's magnetic field behaves. Sometimes, fluctuations in granulation hint at deeper instability beneath the surface. For example, unusual patterns in granulation might signal the coming of sunspots or larger updrafts, which feed into active regions. Though it might seem like a simple visual feature, granulation is a vital part of the Sun's energy cycle. It marks the end of a process that begins in the Sun's core, where energy takes hundreds of thousands of years to emerge. Each granule is a sign of the balance between gravity, thermal pressure, and magnetism. Its size and lifespan are determined by the properties of the Sun's plasma, like viscosity and conductivity. Instruments like the Solar Optical Telescope SOTE aboard the Hinode satellite and the Daniel K. Inouye Solar Telescope DKS in Hawaii provide ultra-high-resolution images of these structures. These instruments capture how the granulation changes within seconds, giving us a glimpse into the chaotic nature of the sun's surface. Granulation also interacts with larger phenomena like shock waves from flares or magnetoacoustic waves, linking the sun's surface to its entire atmosphere. At the core of the sun's magnetic activity is the solar dynamo, the force that drives the sun's magnetic field. This dynamo is far from a static system. Instead, it's a complex process where plasma motions within the sun interact with its conductive properties. The solar dynamo is located in the sun's convective zone, where columns of plasma rise and fall continuously, dragging magnetic field lines along with them. As these flows stretch and twist the field lines, the sun's magnetic field grows in complexity. The sun's rotation plays a key role in shaping this dynamo. The sun doesn't rotate as a solid body. Different parts of it rotate at different speeds. At the equator, it takes about 25 days for the sun to complete one rotation. At the poles, however, it takes about 35 days. This uneven rotation causes shear zones in the sun's internal structure. The strongest shear zone, known as the tachocline, lies between the radiative and convective zones. Here, the magnetic field is amplified and reorganized, transforming the sun's global diepolar field into more complex structures, which eventually emerge as sunspots and magnetic arcs. This process is what powers the sun's 11-year cycle. Every cycle, the sun's magnetic field reverses, its dipolar field distorts and cancels out, only to be reborn in the opposite direction. This is the heart of the solar dynamo at work. When solar activity is at its peak during solar maximum, sunspots, flares, and coronal mass ejections, CMEs erupt in force. During solar minimum, activity slows, but the dynamo doesn't stop. It continues to reorganize, preparing for the next reversal. Scientists use three-dimensional magnetohydrodynamic simulations to understand how convective flows, rotation, and shear create this dynamic magnetic field. These simulations help recreate the formation of solar cycles, the emergence of active regions, and the unpredictable nature of prolonged solar minimums. Even small changes in the sun's internal conditions, like fluctuations in the depth of the tachocline or the intensity of convection, can significantly affect the solar cycle. That's why understanding the solar dynamo is key to predicting future solar activity and managing space weather risks. Despite decades of research, the solar dynamo still holds many mysteries. For example, it's unclear why certain solar cycles are weaker or why prolonged solar minimums occur seemingly unpredictably. Some theories suggest that non-linear feedback between the magnetic field and convection could cause chaotic variations in solar activity. Other studies focus on the role of meridional currents, which move magnetic fields between the poles and the equator, and how they might influence the dynamo's behavior. The solar dynamo is not unique to our star. Any body with convection and rotation, from planets like Jupiter to red dwarf stars, can generate magnetic fields in similar ways. However, the solar dynamo is the most well-documented and studied of all. The relative stability of solar irradiance depends on the dynamo's balance. When the dynamo enters a stable phase, the sun's dipolar field dominates. When it destabilizes, we see surges and rapid changes in solar activity, such as large sunspot minimums and maximums. One of the most striking features of the sun's rotation is its differential nature. The sun's equator rotates much faster than its poles, about 25 days at the equator compared to 35 days at the poles. This difference in rotation speeds creates shear zones within the sun's internal layers. This uneven rotation is directly tied to the sun's internal structure, as the sun is made of plasma, not solid material. The movement of this plasma is influenced by pressure gradients, magnetic fields, and Coriolis forces, leading to complex rotational dynamics. This differential rotation is key to the solar dynamo. As the equator moves faster than the poles, it creates shear forces between layers that twist the sun's magnetic field lines. This twisting forms the sun's toroidal field, which is responsible for most of its magnetic activity. The transition zone between the sun's radiative zone and convective zone, called the tachocline, is where the shear is most intense, and it's here that the magnetic field is organized into coherent structures. Differential rotation also explains the migration of sunspots throughout the solar cycle. Sunspots typically appear at mid-latitudes and gradually move toward the equator over time. This migration follows a predictable pattern that's visualized in the famous butterfly diagram. The interaction between rotation and convection can cause variations in how sunspots appear during the cycle. In some solar cycles, the latitudinal shift of sunspots happens faster or more asymmetrically, indicating changes in the sun's rotation profile and magnetic field strength. The effect of differential rotation extends deeper into the sun, especially at the base of the convective zone. Here the rotation profile is more uniform, and understanding this transition is a major challenge for solar models. Simulations of global convection show that even slight changes in rotation speed can trigger major reorganizations of the sun's magnetic field. Rotation isn't just a result of the sun's internal structure, it's also a key factor that shapes the sun's magnetic behavior. Instruments like the Helioseismic and Magnetic Imager, HMI aboard the Solar Dynamics Observatory, SDO, provide continuous data on the sun's rotation. This data is crucial for predicting the emergence of active regions and monitoring the sun's magnetic cycle. The study of differential rotation extends beyond our sun. Other sun-like stars also experience differential rotation, fueling their magnetic activity cycles. By comparing the solar cycle with those of other stars, scientists can better understand whether the sun's behavior is typical or exceptional. During periods of grand minimums, such as the Maunder minimum, the sun's differential rotation pattern may change. The absence of sunspots and the prolonged quiet period suggest that the sun's internal engine has slowed down or reorganized. This hypothesis is still under investigation, but it highlights the importance of understanding how changes in the sun's internal structure affect its activity cycle. For centuries, the far side of the sun was a mystery. As the sun rotates every 27 days, only one hemisphere is visible from Earth at a time, leaving a significant gap in solar forecasting. This limitation was overcome with NASA's STEREO mission in 2006, which launched two nearly identical spacecraft into solar orbits ahead of and behind Earth. These spacecraft captured stereoscopic images of the sun, enabling the first 3D mapping of its entire surface. By combining data from stereo and Earth-based observations, scientists can now construct near-complete maps of the sun's surface, improving our ability to predict solar activity and space weather. For the first time, space weather forecasters could track active regions on the far side of the sun, gaining valuable insight into their potential impacts before they rotated into view from Earth. This new capability improved solar models significantly. Forecasters could now observe large sunspots or magnetic regions from the far side for days, allowing them to assess the risks of coronal mass ejections, CMEs, and planned satellite protection more effectively. Instruments aboard the STEREO spacecraft like EUV images, coronagraphs, and heliospheric images provided a comprehensive view from the sun's surface to the space beyond, enabling detection of flares, CMEs, and their evolution from unique angles. STEREO also validated helioseismology techniques, which had previously been used to infer far-side activity based on acoustic waves. These direct observations confirmed many of those detections, refining seismic models. During its peak, the STEREO mission offered nearly full solar coverage, and even when Earth couldn't see a part of the sun, the two spacecraft could work together to piece the missing information together. This was especially crucial during periods of solar maximum, when active regions were abundant. Although STEREO B was lost in 2014, breaking the 3D coverage, STEREO A continued to operate, providing one side of the sun's view. In 2023, it briefly returned to Earth's vicinity, offering an opportunity to calibrate its instruments with newer missions like Solar Orbiter. Future missions aim to restore full far-side monitoring. Placing a spacecraft at the Earth-Sun LLA5 point would offer a continuous side view of the sun, bridging the observational gap and ensuring a permanent early warning system for space weather. This global solar mapping isn't just academic, it's essential for forecasting models like WSAN-LIL, which simulates solar wind and CME propagation. Knowing what's happening on the far side of the sun improves our ability to predict geomagnetic storms and their effects on Earth systems. Monitoring the far side also provides crucial data for understanding the sun's magnetic cycle. Active regions on the far side contribute to the sun's overall magnetic flux and influence the solar dynamo's evolution. Without data from this region, solar models remain incomplete. Instruments like GOENG and SOHO complement space-based observations with Earth-based helioseismic data, creating a hybrid network that maximizes coverage even during gaps in spacecraft availability. As solar activity intensifies toward the peak of each cycle, awareness of the far side becomes increasingly important for protecting power grids, communication systems, and astronauts. The additional lead time offered by global solar mapping can make all the difference in mitigating the impact of space weather events. Launched in 2010, NASA's Solar Dynamics Observatory SDO has completely transformed our view of the sun. Unlike earlier missions that were limited by a narrow range of wavelengths or low temporal resolution, SDO provides full disk imagery in multiple ultraviolet bands, capturing extraordinary detail with high cadence. The Atmospheric Imaging Assembly AIA aboard SDO takes images in 10 different UV and extreme UV channels, each one corresponding to different layers of the solar atmosphere, from the chromosphere to the corona. This multi-wavelength approach reveals how solar features behave at various energy levels, providing a deeper understanding of the sun's dynamic activity. A single solar flare, for example, can look completely different at 171 angstroms compared to 335 angstroms. Each wavelength uncovers a unique piece of the energetic puzzle, allowing scientists to observe the sun's behavior in stunning detail. With SDO capturing one image every 12 seconds, producing over a terabyte of data daily, it can resolve features as small as a few hundred kilometers. This precision allows researchers to track dynamics within coronal loops, and even monitor the motion of granulation on the photosphere. Another key instrument on SDO is the Helioseismic and Magnetic Imager, HMI, which measures the sun's magnetic field and tracks Doppler shifts in surface oscillations. This data is critical for tracking sunspot evolution and supports helioseismology studies. Together, these instruments provide an unparalleled toolkit for studying solar variability. Researchers can now correlate changes in the sun's magnetic field with ultraviolet flares, trace filament eruptions from the chromosphere to the corona, and monitor the origins of CMEs in real time. SDO has been instrumental in advancing space weather forecasting by offering high-resolution, time-lapsed views of flare development and other solar phenomena. It significantly improves our ability to predict when and where solar storms are likely to originate. The imagery captured by SDO is not only valuable to scientists but also to the general public. Its stunning color composites and time-lapse videos have helped make the sun more visible and dynamic to audiences around the world, blending science with wonder. From a scientific perspective, the ability to simultaneously monitor temperature-specific layers of the sun's atmosphere is a game-changer. It allows for time-resolved studies of energy transfer and plasma flows, which are essential to understanding coronal heating and flare mechanisms. The data gathered by SDO feeds directly into models of solar irradiance, the energy received from the sun at various wavelengths. These models help quantify how variations in solar output affect Earth's upper atmosphere, climate, and satellite orbits. SDO has also made significant contributions to solar cycle analysis by tracking how active regions emerge, migrate, and decay over the course of the solar cycle. It has helped refine our understanding of the solar dynamo, shedding light on its rhythmic behavior and underlying processes. Despite its extensive data output, SDO has maintained excellent calibration and stability, ensuring its decadal-long archive is invaluable for longitudinal studies of solar phenomena. This consistency is crucial as upcoming missions like Solar Orbiter and DKIST can use SDO's foundational data to compare and calibrate their own observations. The success of SDO has set a new standard for solar observation. With its combination of breadth, depth, and resolution, SDO has redefined how we observe the sun, transforming it from a distant static star into a dynamic, living laboratory. The sun's outer atmosphere, the corona, is normally invisible to the naked eye because its faint glow is drowned out by the sun's brilliance. Observing it was only possible during rare total solar eclipses until the launch of SOHO in 1995. SOHO revolutionized solar observation by using coronagraphs to simulate eclipses, blocking the sun's bright disk with an artificial occulter. This allowed scientists to observe the faint coronal structures in real time, uncovering massive loops, streamers, and plasma outflows. SOHO's coronagraphs have been key in tracking CMEs, vast clouds of solar material ejected into space. The Large Angle and Spectrometric Coronagraph, LASCO, on SOHO show is divided into multiple channels, each capturing different scales and brightness levels of the corona. This multi-tiered approach gives a complete picture of coronal dynamics, from small outbursts to massive reorganizations. One of LASCO's most critical contributions is the detection of halo CMEs, circular expansions that indicate a CME is heading directly toward or away from Earth. These events demand immediate attention from space weather forecasters. Before SOHO, CME detection was sparse and lacked structure. The coronagraph revolutionized this by documenting and measuring every significant ejection. Now each major solar ejection is recorded, analyzed, and modeled. SOHO has made the invisible corona a continuous part of scientific observation, revealing dynamic features like coronal waves and streamer blowouts. These phenomena, linked to magnetic reconfigurations, demonstrate the connection between the sun's interior and its outer atmosphere. SOHO's long-term presence has allowed us to compare CME behavior across solar cycles, enhancing our understanding of how ejections evolve over time. The data from SOHO is also used in planetary defense, helping to forecast the impact of space weather on satellites, astronauts, and power systems. By providing hours or even days of warning, SOHO acts as a critical part of our technological shield against solar storms. Its legacy has inspired coronagraph designs for future missions like STEREO and Solar Orbiter, ensuring that the next generation of solar observers benefits from the lessons learned during SOHO's decades of operation. Even as new missions are launched, SOHO continues to be an invaluable asset for monitoring coronal mass ejections, CMEs, and solar activity. It holds a prime position in space, located at the L1 Lagrange point, roughly 1.5 million kilometers from Earth in the direction of the Sun. This unique location, where the gravitational forces of both the Earth and the Sun perfectly balance with the orbital motion of spacecraft, allows for continuous observation without disruption. From this vantage point, SOHO can provide uninterrupted data on solar events. Unlike Earth-based telescopes, which are affected by the planet's shadow or atmospheric distortion, instruments at L1 can observe the Sun's activity 24/7 without any interference. This makes it the perfect spot for monitoring solar phenomena like CMEs, which can have significant impacts on Earth's space weather. When a CME erupts, it travels through space and typically reaches the L1 point about 30 to 60 minutes before it hits Earth. Instruments stationed there measure the CME's magnetic field, density, speed, and orientation in real time, providing essential information that helps predict its potential impact. The AC and DSO-VR spacecraft, both positioned at L1, play a key role in these efforts. Their instruments supply crucial data that power early warning systems for solar storms. By analyzing the magnetic properties of a CME, scientists can estimate whether it will trigger a geomagnetic storm, offering critical information to protect infrastructure like satellites, communication systems, and power grids. LALS-1's strategic location has revolutionized space weather forecasting. Thanks to the data gathered at L1, agencies can send out alerts with just minutes to spare, helping mitigate damage caused by solar storms. Beyond space weather, L1 is also home to solar observatories. SOHO, for example, uses its steady position to conduct coronagraphy, studying the outer layers of the Sun, and gather long-term data without interruptions. The position of L1 provides essential benefits for both space weather monitoring and solar research. It allows scientists to model the solar wind's behavior and forecast the arrival and intensity of CMEs, especially during periods of solar maximum. The L1 point also provides a rare perspective, enabling spacecraft to observe both the Earth and the Sun simultaneously, which is valuable for missions studying Earth's reaction to solar activity, such as changes in the ionosphere, auroras, and the expansion of the thermosphere. As technology continues to evolve and our reliance on satellites and space-based systems grows, the L1 point will only become more crucial. It acts not only as a watch point but as an early warning system that keeps us ahead of solar activity. Its data informs everything from satellite operations to infrastructure management, making L1 a key player in protecting our technological infrastructure. Laoban's role extends beyond monitoring space weather. It's also a valuable resource for future space missions. Its location allows spacecraft heading toward Mars or other deep space destinations to use L1 for gravity assists, communication relays, or even staging missions. This makes L1 more than just a point of observation. It's a critical node in the ongoing development of space exploration and defense. As our dependence on space-based technology increases, Laoban's significance will only grow. It's not just a stationary point in space, it's a critical component of Earth's defense against solar storms, a vital resource for space science, and a hub of information that keeps our planet connected to the broader universe. Sunrise, a balloon-borne solar observatory, offers a unique window into the sun's magnetic activity. By observing areas where magnetic fields emerge and reconnect, Sunrise provides valuable insights into how energy moves from the sun's surface upward into its atmosphere. Equipped with a range of specialized instruments like a UV filter imager, a magnographer, and a spectropolarimeter, it captures not just intensity but also magnetic fields and Doppler shifts, key data points for understanding the sun's behavior. The data collected by Sunrise has been instrumental in bridging the gap between theoretical models and real-world solar phenomena. Its observations of small-scale magnetic interactions have validated and refined simulations of solar convection and the evolution of the sun's magnetic fields. One of the key benefits of using balloon-based observatories like Sunrise is their cost efficiency. While space missions can cost billions of dollars, the Sunrise balloon offers high-end solar science at a fraction of the price, and its modular design allows for upgrades between flights. Sunrise has completed several successful flights, each lasting 5 to 6 days. After each flight, it returns a wealth of data that can be analyzed for months. New versions of the payload are already in development, with enhanced sensitivity to push the boundaries of solar research even further. This mission also highlights the power of high-altitude platforms for solar observation. Unlike satellites, which are fixed in orbit, Sunrise offers mobility, allowing it to conduct precise observations of the sun's surface over a wide range of locations. It's perfect for testing new technologies in solar research, making it an ideal platform for innovation. In addition to its scientific contributions, Sunrise also plays a key role in the training of engineers and researchers. Balloon missions like this serve as testing grounds for new designs, which can later be adapted for orbital missions. Despite the limited duration of each flight, Sunrise continues to provide invaluable data, offering some of the most detailed views of the sun's magnetic structures. From its high-altitude vantage point, Sunrise captures the finest details of solar activity, offering a perspective that ground-based observatories simply can't match. It proves that with the right optics, timing, and elevation, even balloon-based missions can provide groundbreaking insights into the sun. The sun's journey to send light to Earth is not a direct one. In fact, it takes between 10,000 and 170,000 years for photons to travel from the sun's core to its surface. This immense delay is due to the sun's dense, opaque interior. Inside the core, energy is generated through nuclear fusion, converting hydrogen into helium and releasing gamma rays. But these photons can't escape easily. They are repeatedly absorbed and re-emitted by particles, a process known as radiative diffusion. Imagine trying to walk straight through a crowd that constantly shifts your direction. That's what light does inside the sun. Once these photons finally reach the photosphere, the sun's outermost layer, everything changes. Here the sun becomes transparent enough for light to travel freely. From this point, sunlight travels through the vacuum of space and reaches Earth in just 8 minutes and 20 seconds. This stark contrast highlights the sun's core as more of a radiant fog than a straightforward furnace. The light is trapped and scattered, slowly creeping its way outward. Interestingly, the journey of light differs based on where it starts. The path through the sun's equator is not the same as the path through its poles, due to variations in density and magnetic interactions. But no matter where the photon starts, its journey is a random walk, meaning it is constantly redirected. This process explains why the sun's surface brightness remains so stable over time. The long diffusion time acts as a smoothing filter, averaging out fluctuations in energy release. This stability plays a key role in maintaining Earth's climate and life. Understanding this diffusion process also helps us model stellar evolution. The time it takes for energy to transport affects how stars age, balance pressure against gravity, and respond to changes in fusion rates. Modern simulations use Monte Carlo methods to simulate these random walks and predict how the sun's spectrum and brightness will appear. These models are validated by data from space missions like SOHO and heliosismic observations, which provide critical measurements of solar activity. The timescale of energy transport also sets a limit on how quickly the sun can react to changes in its core. Any fusion rate changes would take thousands of years to show up in sunlight. While photons take eons to escape, neutrinos, particles created in the same fusion reactions, take mere seconds to leave the core. These particles interact so weakly with matter that they can travel through the sun and Earth almost undisturbed, offering another fascinating clue about the sun's inner workings. The sun's convection process is a key factor in maintaining its luminosity and stability. Though chaotic, the system naturally organizes itself to keep energy flowing upward and magnetic fields spreading outward. One of the most intriguing features of the sun's surface is the appearance of sunspots. These dark patches are cooler than the surrounding photosphere, with temperatures around 3,500 degrees Celsius compared to the sun's typical 5,800 degrees Celsius. Despite their lower temperatures, sunspots are still brighter than a full moon as seen from Earth. These regions are zones of intense magnetic activity, where concentrated magnetic fields suppress convection and reduce the upward flow of heat, causing the area to cool and appear darker. Sunspots are dynamic. They evolve over hours to weeks, growing, shrinking, and changing as their magnetic fields twist, reconnect, and shift. Large sunspots can span tens of thousands of kilometers, sometimes big enough to engulf Earth several times over. Each sunspot consists of two main components, the umbra, which is the darkest and most magnetically intense part, and the penumbra, a lighter filamentary region that surrounds it. The penumbra also features inclined magnetic fields and horizontal plasma flows, known as Evershed flows, that further define the spot structure. Beneath the surface, sunspots have complex subsurface features. Heliosismic measurements show how sound waves are deflected and slowed by these areas, providing valuable insights into the sun's magnetic architecture and plasma flows. Sunspots often appear in pairs or groups, reflecting the magnetic polarity of the region. Magnetic field lines arch outward from one sunspot and re-enter through another, creating loops that store immense amounts of energy. When these magnetic fields suddenly release their energy, they can trigger flares or coronal mass ejections, CMEs. The distribution of sunspots follows a predictable pattern over the course of the solar cycle. At the beginning of the cycle, they appear at mid-latitudes, but as the cycle progresses, they migrate toward the equator, forming a pattern known as the butterfly diagram. Sunspot numbers rise and fall in an approximately 11-year cycle, closely tied to changes in the sun's magnetic field strength and polarity. During periods of solar maximum, sunspots are numerous and often large. At solar minimum, they may disappear entirely. Sunspots are a reliable indicator of solar activity. When sunspot numbers are high, solar storms, auroras, and radiation events tend to increase. These events can disrupt satellites, radio communication, and power grids on Earth. The Maunder minimum, a period in the 17th century with very few sunspots, coincided with a cooler climate in parts of Europe and North America. While the exact connection remains debated, the correlation highlights the importance of sunspots as markers of solar activity. Sunspots also offer a way to measure the sun's rotation rate. As they rotate with the sun, scientists can track their movement across the solar disk to learn that the sun's equator rotates faster than its poles. This discovery has provided important insights into the sun's internal fluid dynamics. To measure the magnetic fields of sunspots, scientists use a technique called Zeeman splitting of spectral lines, which was pioneered in early solar observatories and is still in use today. These measurements show that sunspots can have magnetic field strengths thousands of times greater than Earth's. High-resolution imaging from instruments like the Daniel K. Inouye Solar Telescope (DKS) allows us to observe intricate details of sunspot structures. These images reveal the fine-scale features of magnetic suppression and convective flows within the sun's outer layers. While sunspots appear dark, they provide a visible signature of the sun's magnetic forces at work. They mark areas where magnetic fields rise from the sun's interior, disrupt convection, and reshape the energy emerging from below. Although sunspots dim parts of the sun, they illuminate our understanding of the sun's complex magnetic behavior. Solar flares are another dramatic expression of the sun's magnetic activity. These sudden, intense eruptions of electromagnetic radiation release massive amounts of energy, heating plasma to tens of millions of degrees and accelerating particles to near-light speeds. The flare process begins with magnetic reconnection, when twisted or stressed magnetic field lines suddenly break and reconnect in a more stable configuration. This rearrangement releases enormous amounts of energy, which powers the flare's explosive effects across the electromagnetic spectrum, from radio waves to gamma rays. Most of the flare's energy is emitted as extreme ultraviolet EUV and X-rays, which ionize Earth's upper atmosphere and can disrupt radio communication and GPS signals. Hard X-rays are produced when high-energy electrons collide with dense material in the lower atmosphere, while gamma rays may arise from nuclear interactions involving accelerated protons. Flares can last anywhere from minutes to hours, and they are classified by their peak X-ray brightness, with the strongest flares being classified as X-class. These powerful events can release more energy than millions of hydrogen bombs, although only a fraction of that energy reaches Earth directly. Much of it is contained in the solar atmosphere or carried away by energetic particles. Flares are often associated with sunspot regions where magnetic fields are most concentrated and complex. Not all flares are accompanied by CMEs, but when they occur together, the flare provides an early warning, a flash of light that precedes the slower-moving wave of particles. Solar flares also emit bursts of energetic particles known as solar energetic particles (SEPs), which can reach Earth within minutes, posing a risk to satellites, astronauts, and high-altitude aviation. The study of solar flares combines imaging, spectroscopy, and radio observations. Instruments like SDOAIAA and RESI have provided stunning images of flare dynamics, helping scientists understand how flare energy is transported and deposited. One of the key questions remains how this energy is divided. How much goes into heating, particle acceleration, and wave generation? While the answer is still under investigation, flares serve as a natural laboratory for studying plasma physics, providing examples of reconnection, shock formation, turbulence, and particle acceleration that occur not just in the sun but across the universe. Coronal mass ejections, CMEs, are another major solar event, though they unfold more slowly than flares. CMEs are massive eruptions of plasma and magnetic fields from the sun's corona, launching billions of tons of solar material into space at incredibly high speeds. A typical CME contains twisted magnetic flux ropes filled with charged particles. These structures form when the sun's magnetic field can no longer contain the stress building up in the corona. When the magnetic field destabilizes, it triggers an explosion, sending a wave of plasma and magnetic fields into the heliosphere. CMEs vary in size and speed. Smaller CMEs may barely reach interplanetary space, while large ones can travel at speeds over 3,000 kilometers per second, reaching Earth in less than 15 hours. Most CMEs, however, take 1 to 3 days to travel from the Sun to Earth. As they travel through space, CMEs interact with the solar wind, and their magnetic fields and shock fronts can either compress or pass harmlessly by Earth's magnetosphere, depending on their orientation. If the CME's magnetic field is opposite to Earth's, it can reconnect with our magnetosphere, triggering geomagnetic storms that disrupt satellite operations, power grids, and communication systems. To observe CMEs, scientists use coronagraphs, which block the sun's bright disk to reveal the faint outer corona. Instruments like SOHO's LASCO and the Stereo spacecraft have captured thousands of CMEs, helping scientists catalog their structure and direction. Halo CMEs, which expand in all directions, are often directed toward Earth, but their symmetry can also suggest they're moving away from us. CMEs that don't show strong coronal signatures are known as stealth events, and observing them requires multiple spacecraft to get the full context. The origins of some CMEs are difficult to pinpoint, which makes them particularly challenging to forecast. While they may not produce dramatic flares, they can still have significant space weather effects. The mass ejected in a CME can exceed 101210 circumflex 12 K, roughly equivalent to the mass of Mount Everest. When combined with their high speed, CMEs possess kinetic energy comparable to several days' worth of global energy consumption. Shock waves from fast-moving CMEs accelerate particles ahead of the plasma cloud. These solar energetic particles (CEPs) reach Earth before the main plasma, and they can damage electronics or pose radiation risks to spacecraft and astronauts. The arrival time of a CME is predicted using heliospheric models that simulate how the event propagates through the solar wind. Instruments like AC and DSCOVR, stationed at the L1 point, provide real-time upstream measurements which help refine predictions and issue warnings just minutes before the CME reaches Earth. However, the impact of a CME depends on timing, orientation, and existing conditions in Earth's magnetic field. For example, even a moderate CME can cause severe disruption if Earth's magnetic defenses have been weakened by a previous solar event, a phenomenon known as preconditioning. One of the most beautiful displays of space weather is the aurora, Earth's neon glow. These captivating lights are the result of solar particles interacting with Earth's magnetic field. When solar wind or particles from a CME reach Earth, they follow the planet's magnetic lines into the upper atmosphere. There they collide with atoms, releasing light in different colors. The majority of these particles come from the solar wind or CMEs, and their interaction with the Earth's magnetosphere directs them toward the polar regions, where they form auroral ovals. The primary colors of auroras depend on the types of atoms involved and the energy of the interactions. Oxygen atoms emit green or red light, while nitrogen atoms produce blue or purple hues. Auroras are most common during periods of high solar activity, when the sun sends more particles toward Earth. Their intensity and appearance vary based on the speed, density, and magnetic orientation of the solar wind. A strong southward magnetic field in an incoming CME, for instance, promotes reconnection with Earth's magnetic field, resulting in more intense auroras. Spacecraft like Themis, along with ground-based cameras, help track the evolution of auroral substorms, brief bursts of brightness that involve magnetic reconfigurations and particle injections in Earth's near-space environment. Auroras are not just beautiful spectacles, they are signals of deeper underlying processes. The ionization and heating of the upper atmosphere caused by solar particles can interfere with GPS signals, radio communication, and over-the-horizon radar, especially near the poles. During major geomagnetic storms, auroras can even extend to lower latitudes. For example, the 1859 Carrington event caused auroras that were visible as far south as the Caribbean, and recent storms have made auroras visible in parts of Europe and the United States. The mechanism behind auroras is governed by magnetohydrodynamics, the study of magnetic fields and charged fluids. Earth's magnetotail, a region that stretches far behind the planet, stores energy that can be released to power auroral displays. The precise triggers for these auroral outbursts are still actively researched, with models suggesting that magnetic reconnection, pressure buildup, and plasma sheet instabilities all play a role in their onset. Satellites like DMSP and NOAA measure the flux of particles entering the atmosphere, while ground magnetometers help provide a complete picture of space weather conditions. Auroras are not unique to Earth. Other planets with magnetic fields and atmospheres also experience auroras. Jupiter, for example, has auroras driven by both the solar wind and internal processes related to its moons. These cosmic displays highlight how magnetic interactions can vary across different planetary systems. For indigenous cultures in the Arctic, auroras have long been viewed as spiritual phenomena. Modern science now frames them as visual representations of the invisible, high-energy forces surrounding our planet. Auroras also intersect with our daily lives in subtle ways. During solar storms, high-latitude airline flights often adjust their routes and radio frequencies to mitigate the risks posed by ionization in the auroral zones. These operational protocols underscore how space weather can influence our infrastructure in unexpected yet important ways. Every aurora is a reminder of Earth's dynamic relationship with the Sun, a cosmic conversation between solar wind and magnetic field, and in that shimmering glow we catch a glimpse of the fundamental physics at play, the shape of our planet's magnetic shield, and the far-reaching influence of the Sun.